You'll learn about layer 4 of the OSI model, the transport layer, in this lecture. So layer 4, transport layer, it provides transparent transfer of data between hosts and is responsible for end-to-end error recovery and flow control. But as you'll learn as we go through the lecture, that is not mandatory. So maybe the layer 4 protocol will support error recovery and flow control, maybe it won't. You'll see the implications of that as we go through. So in flow control, it's the process of adjusting the flow of data from the sender to ensure that the receiving host can handle all of it. So if the sender is sending too quickly, maybe because we've got faster network connections on that side, and it's sending more than the receiving host can accept, then if flow control is enabled, the receiving host will have a mechanism to signal back to the sender telling it to slow down. Another thing that is supported at layer 4 is session multiplexing. This is a process by which a host is able to support multiple sessions simultaneously and manage the individual traffic streams over a single link. So let's take a look at how that works. So the example here, I've got a sender on the left, and there's going to be a couple of receivers over on the right. The sender sends some email SMTP traffic to the top receiver on port 25. And it also sends some web traffic on HTTP port 80 to the bottom receiver, and it's also sending email traffic on port 25 to the bottom receiver as well. So you can see from the sender on the left, we've got 3 sessions from it. The top receiver on the right, we've got 1 session, and on the bottom receiver, we've got 2 sessions. It's layer 4, the transport layer, that is responsible for tracking and keeping control of the different sessions on a host. We have port numbers. So going back to that previous example again, you see we've got 2 sessions going from the sender on the left to the bottom receiver on the right. One of them is web traffic, the other session is email traffic. So when the traffic comes into the receiver, how does it know which application this traffic is for? Is it for its web server application, or is it for its email server application? The way it knows is with the layer 4 port numbers. For example, HTTP web traffic uses port 80, SMTP email uses port 25. We'll talk about some of the other common port numbers at the end of the lecture as well. The sender also adds a source port number to the layer 4 header as well. The combination of source and destination port number can be used to track sessions. So let's see how that works as well. So here we've just got 1 sender on the left, the receiver on the right, and we're sending web traffic again here. So the sender, it sends it with a destination port of port 80, the standard port for web traffic, and it will use a random source port number above 1024. In our example, it's using source port 1500. So we've got a connection between the sender and the receiver. When the receiver sends traffic back, it will flip the source and destination port numbers around. So it will use port 80 as its source now, and the destination will be port number 1500. This is how stateful firewalls are able to keep track of connections as well. Imagine that rather than a switch in the middle there, if it was a firewall, and we had a rule in the firewall that said traffic is allowed out from the sender on the left, out to the network on the right, but traffic is not allowed from the right to the left unless it was initiated from the sender, if you manage to follow that. Well, in that case, on the firewall, we're allowing traffic from the sender to the receiver. That traffic is allowed outbound. When the return traffic comes back, the firewall could see, based on the source and destination port numbers, oh, this is return traffic going back to that sender again, so I'll allow this traffic to come through. If the traffic had been initiated by the host on the right, it would not allow that traffic. Okay, so that's how stateful firewalls work. Our 2 most common protocols at layer 4 are TCP, which is the Transmission Control Protocol, and UDP, which is the User Datagram Protocol. TCP is connection oriented. As we go through the rest of this lecture, you'll see that a lot of the main characteristics of TCP and UDP are opposite each other. And after I've explained both protocols, I'll explain why that is. So TCP, it's connection oriented, meaning that once a connection is established, data can be sent bidirectionally over the two hosts over that connection. TCP carries out sequencing, so it includes sequence numbers in the traffic to ensure that segments are processed in the correct order and none are missing. So when traffic comes into the receiver, it can look at the sequence number and it can use that to make sure that it assembles the traffic in the correct order again. It can also check from the sequence numbers if a segment was lost in transit as well. TCP is reliable. The receiving host sends acknowledgements back to the sender. So based on the sequence numbers, the receiver can see if all the traffic has come in. If any traffic is being lost in transit, then it will tell the sender that that happened. The way it does it is by not sending an acknowledgement back to the sender. When a sender realizes that traffic has been lost, it will resend that traffic again. TCP can also perform flow control as well. So if the sender is sending at a rate too high and the receiver can't handle it, the receiver can signal back to the sender telling it to slow down. So TCP, it's a connection-oriented, reliable protocol. The way that that connection is set up between the two hosts is it uses the TCP three-way handshake. So here we've got the sender on the left is going to initiate the connection. It sends a SYN, a synchronized message, over to the receiver on the right. When the receiver receives that, it will send a SYN-ACK back, so a synchronized acknowledgement, and then finally, to complete the connection, the sender will send an acknowledgement. We now have the connection set up between the two hosts, and they can send traffic over it. The next thing I'm going to show you is the makeup of the TCP header. But just before I show you, I wanted to give you a quick reminder from the previous lesson about how a packet is composed. So here we've got the sender on the left, the receiver on the right, and we're going to send some traffic over there. So first off, as the sender is composing the packet, it will put in the layer 7 information. It will then encapsulate that with the layer 6 header. It then gets encapsulated with the layer 5 header, then layer 4 header, then layer 3 header, layer 2 header, and then we send it onto the physical wire. So what you're going to see in the next slide is how that layer 4 header is composed, what comprises it. And here's how it looks. So we've got the source port and the destination port numbers, as we spoke about just there earlier. We then have the sequence number and the acknowledgement number. We have a header length, a reserved field, which is for any reserved information later, code bits, window, which can be used for flow control, a checksum, which can be used to check and see if the traffic got corrupted in transit. We've got an optional urgent part of the header there as well. We can add other options, and then we've got the data. So you see there's quite a lot that goes into the TCP header. We'll contrast that with the UDP header coming up in a minute. So let's talk about UDP now. UDP is the user datagram protocol, and it sends traffic best effort, meaning we don't have the connection, we don't have reliability. The sender just makes up the packet, sends it over to the receiver, and hopes that it's going to get there. So at UDP, it's not connection oriented. There's no handshake connection set up between the hosts. It doesn't carry out sequencing to ensure segments are processed in the correct order or missing. It's not reliable. The receiving host does not send acknowledgements back to the sender, does not perform flow control. So you know how I just said that the sender will send the traffic and hope it gets there? We can still have error detection and recovery for this traffic, but if it is required, it's going to be up to the upper layers, higher up to the application level to actually provide that. It's not going to be provided by UDP. So looking at the UDP header, you'll see there's much less fields in here. All we have is the source and destination port, the length, and a UDP checksum, and the data. So you can see by comparing the UDP header and the TCP header, there's much less overhead with UDP. which leads us into where TCP or UDP would be used. Now this is up to the designer of the application. Whenever a designer designs an application, they can choose whether it's going to use TCP or UDP for its transport. They will typically choose to use TCP for traffic which requires reliability. But real-time applications such as voice and video can't afford that extra overhead of TCP, so they would use UDP. Voice and video, it's very sensitive to delay. You've probably watched TV before, you've seen a news report where the newscaster's doing it over a satellite phone, and you can see it's very laggy because satellites are famously high latency connections. So voice and video, it's very sensitive to latency. We don't want to use TCP for real-time traffic like that because the extra overhead is going to slow it down and it's going to affect the quality. So for real-time traffic that's sensitive to delay, we'll usually use UDP. For other applications, we'll use TCP. And because there's a lot more other applications in voice and video, TCP is the most commonly used layer 4 transport. There are some applications that can use both TCP and UDP as well. You'll see an example on the next slide. So here we're going to look at some of the common applications and their destination ports. For applications that use TCP, we've got FTP, the file transfer protocol, that uses port 21. Secure Shell is on port 22. Telnet port 23. HTTP web traffic is on port 80, and HTTPS encrypted web traffic is on port 443. Some UDP protocols, we've got TFTP, the trivial file transfer protocol uses port 69, and SNMP, the simple network management protocol, uses port 161. And the best known application that can use both TCP and UDP is DNS on port 53. There are some other voice and video signaling protocols that can also use both TCP and UDP as well. Okay, so that was it. That was our layer 4 transport layer lecture. I'll see you in the next one.